Online.
Yes. Okay, so we can start. So it's a pleasure to have Antoine Bourget from IPhT. So I don't know if a formal presentation of Antoine. Probably not. It's really an expert in string theory, quantum physics. So that and will tell us about symmetry and topology in quantum physics.
Thank you very much for the opportunity to give these lectures here. Thank you all for coming. The room is almost full. Now it will maybe be full. So, so it's really nice. So yeah, I will try to talk about this topic, symmetry and topology. So just to be clear, this course, so in the title, which now disappeared, but which was there, it was written for pedestrians, and that's really what I will try to follow. So it's really designed as a course for people who have not seen what these things are for the last 10 years, say. So if you know nothing, probably you will be able to understand what I will say and understand some of the feature of these fields. If you know some of it, then you will probably learn many things in a slightly different way from what you've known otherwise. If you're an expert, then certainly you will not learn anything. Maybe you can teach me things, because I should say right now that I'm not the biggest expert in this field. But you should see this lecture as a view from a slight outsider to this topic. My specialty, as Francesco said, is more in string theory, supersymmetry, and so on. And there will be none of this here. So I will try my best to not have anything supersymmetric, anything related to string theory, no quantum gravity, nothing. So yeah, ask questions whenever you like. And I will begin with a little introduction. So in case you've missed it, this theme, so the notion of symmetry, is of course very old fundamental concept in physics. And the point is, in the last 10 years, about 10 years, it has been revived. So a lot of the known things have been reformulated in a slightly different language. And this language allows for generalization. And this generalization, the idea is everything you could do with what you thought symmetries were more than 10 years ago, you can more or less do them also with the more general framework. And it brings new insights and new tools to study. I will focus on quantum field theory, but there could be also application to statistical physics, condensed matter, quantum gravity, and many. It's actually any place where symmetry is a thing, these tools can be used. So what are these things that symmetry? So why did people study symmetry? Or why do we study symmetry? Yeah, I should say right now, we can say it later, but I can say right now, that the reference for this particular talk, the first talk, is the original paper by Gaiotto, Kapustin, Weber, and Willett in 12 something. Basically, everything I would say here is contained in here. And there are tons of lecture notes and online, so you can just Google generalized symmetries and so on. So I will not mention any here. Okay. So, so why are symmetries used in physics? Well, the first thing is to simplify problems. You have whatever physical problem. Usually physics is complicated, so you look for symmetries to simplify things. In quantum field theory, typically a consequence of such simplifications will be that certain things that, if you didn't know anything, could take any value, they will take very specific value, and due to the symmetry. And well, up to some combination, you can always make these values to be zero. So typically in QFT, these imply some kind of selection rules. So you compute some observables, and you find that it's hard. But then using a symmetry argument, you say, oh no, this should be 0. So that's typically a use of symmetry. Another use, which is more oriented towards condensed matter, is the Landau paradigm. So this basically says that the phases of matter are classified by the symmetries and how symmetries are broken. And this paradigm is supposed to mean that really all phases of matter can always be characterized by some symmetry or its breaking. And then I take a quote from, there is some lecture note by McGreevy, who says, okay, so if you've attended condensed matter talks, theoretical condensed matter talk in the last decade, the speaker always begins by saying that Landau told us that states of matter are classified by symmetry the break. Then, after showing the picture of a donut, they draw this, the speaker explains that in this talk, in contrast, they will discuss a state of matter that goes beyond Landau's limited conception of the world. So yeah, typically this is always discussed in the recent years to say, oh, but actually what I'm doing is beyond that. But that's the whole point of these generalized symmetries. It's to restore this. So we will see that symmetries can be generalized, and all these exotic phases of matter can be put back in this framework, provided you extend what you mean by symmetry. So I will come back to this. The other point is that symmetries typically contain some discrete data. So here I'm a bit vague, but typically imagine that your favorite system has a Z2 symmetry, like spin flip, or well, that's a discrete group. That thing cannot be modified by continuous change of parameters. Or if it changes, then there will be a point in a continuous flow. So for instance, you can think RG flow or flow in the space of parameters. There will be a particular point at which there will be a transition, some phase transition. Otherwise, these discrete data are preserved. So typically, it helps. We'll just say this. And here I'm quite vague, but an example of this discrete data that we will discuss is that of anomaly. So anomaly is, so even the name here is a bit confusing. Anomaly, it looks like something is going wrong, bad, but actually there's nothing bad with an anomaly. That's a perfectly fine feature of a symmetry. And typically that thing is discrete. Even if the symmetry is continuous, like you will have U1 symmetry, the anomaly will be and then you can turn it down. And so, for instance, this leads to the, for instance, anomaly matching, where you compare the UV and the IR of some theory, and if there is an anomaly at some point and the symmetry is preserved, then the anomaly has to be the same, and then it gives constraints. So it gives constraints either on the UV from the IR or on the IR from the UV, depending on your perspective of thing, if you're a model builder or a phenomenologist. So this is the very broad introduction. All of these things will be made precise. That's the goal of this. And then another thing that one might do with symmetries is they can be gauged. So actually, I should say two things. Symmetries can be gauged, and there is also something that some people call gauge symmetry. But in most contexts, when people say gauge symmetry, they don't actually mean gauge symmetry. Typically, in the standard model, there is a gauge redundancy. There is an SU3, there is an SU2. That's a gauge redundancy. There is no gauge symmetry. In some systems, there is a gauge symmetry. We will see some of them today. And then gauge is also a verb. It's an action of gauging. So it produces, you can take a theory with symmetry, say G, some group. That's your starting point. And then you can gauge G, and then you get a new theory. And in the new theory, there is no symmetry G anymore. But there might be something new, which we will study as well. So gauging is a process that takes a theory and outputs a new theory. What else did I want to say? Okay, these are a few things that you can do with symmetry. Now, all of this is with standard symmetries, and the point of these generalized symmetries is to try to apply the same thing, but in a more general framework. As I said, for instance, this Landau paradigm, if you just focus on the basic notion of symmetry that we all have in mind, there seems to be many exceptions to this paradigm. Also, there are selection rules in physical systems that are here, like you compute some correlation function, and then you find that this is 0, but you don't have a good symmetry reason to explain it. But maybe it's because your conception of symmetry was not general enough. So yeah, I don't know what to write. But, then there is this thing here with anomaly. This looks like, as I said, a weird feature of a symmetry. Why are some symmetries anomalous? Why some are not anomalous? And what is exactly the status of that thing? Not completely clear. I mean, it can be made clear, but it sounds like a weird thing on the framework. And then the point will be that we will generalize the concept of symmetry, and we will be able to clarify all of this. So just in one sentence, put it up here. The goal is to generalize the concept of symmetry. In such a way that it becomes more powerful. So for instance, with respect to the second point here, or the fourth point here, so it will we will be able to understand better phases of matter. If you think of gauging as this operation to produce new theories, if we have more symmetries, something much more general, then we will be able to do much more of those things. So in this sense, it's more powerful. And also simpler. So that's, of course, a relative statement. You will tell me at the end if you find it simpler. But the point is, a lot of things which like anomalies will become simpler, gauging will become simpler, selection rules, like everything, we will rephrase that. So that's the goal, to convince you of that. And how do we do that? And I already said it, by generalizing. So yeah, I will try to not make this introduction too long because it's a bit vague, maybe. But still, I want to write the punchline. So the concept of symmetry, I haven't defined it. I have told you what we can do with it, but I still haven't told you what is a symmetry. And that will be actually the point of today's lecture. And the reason why it's not so clear is because it's not easy to define what is an abstract concept. The point is, we start from an intuitive idea. So there is an intuitive idea. It's intuitive, it's physical idea. We see something and we say, yeah, that looks symmetric, or there is some invariance, and we say, yeah, things don't change if I do this or that. So we have this intuition, and we try to formalize. When this is the intuitive idea, and then we want to formalize or axiomatize. And then once we axiomatize, an intuitive idea becomes a mathematical concept. And actually, the idea of symmetry originates in math before physics, because it originates in this idea of permuting the roots of a polynomial and leaving it invariant. So that, as you know, that's why the concept was there in math before. But we can pretend we don't know about this, or if you don't know, then it's good. If you just want to start from the physical idea, then symmetry should be something, some kind of action. It should be some kind of action, which is, well, if you do it twice, then that should also be a symmetry. So you should be able to compose. You should be able to compose symmetry. You should be able to invert symmetry. Like if something is really a symmetry, then if you do it, then you should be able to go back to where you were before. So you compose, you invert. The composition, okay, that's a bit more difficult to see, but the idea is if you have I don't know, some kind of object, and then you act with a symmetry, you get it a bit differently, and then you act again. You'll be able to draw it nicely, but and then you act again. The point is, it should not depend on how you compose the thing. So if you act first with this and this and then this, or you put these two and act with that, it should be associative. So that's the associativity. And of course, doing nothing is also a symmetry of everything. So this is the intuition. But then why did I mention associative? Maybe you didn't think about that. Maybe you say, no, I should not include that. But okay, let's assume we put all this together, and then this I should have written here on the intuitive side, and then the math concept, of course, as you know, is that of a group. So if you say intuitively a symmetry should be something that acts, I can compose, I can invert, and so on, then you're naturally led to the math concept of a group. But what tells you that these were the right actions? Why exactly those? Why not more or less or others? That's a very, very hard question. There is no one is telling you. But somehow this led to a lot of mileage in math, of course, and then in physics. So I think before the 20th century, so up to the 19th century, physicists did not really use the notion of group. They, of course, used symmetry already, but in a simple enough way that they didn't need group theory. But after the 20th century, with Lorentz groups in quantum mechanics and so on, and then even more with particle physics and so on, it became very important to have this group notion. And that's something which is very important as well that I should mention. In principle, having a math concept is not really necessary. You could pretend you don't know it and do everything by hand. So each time you have a symmetry, you could not mention that you have groups, but do without. It's just that at some point, there are things that you realize you do very often, always the same thing. So it's good to do it once and for all, to have a theory, and then you have it. So for instance, a group representation, in principle, you could pretend you don't know what it is, and each time repeat that you have some space on which the group acts and so on. But then that would be really hard to do particle physics if you don't have the concept of group representation. But in principle, you could do it. Okay, so now at the end of this introduction, the idea is that we will, in this lecture, introduce a new form of axiomatization. So we will I mean, not throw everything out of the window, but some of it. But let me just say, we don't want this. The goal is, let's try to find a new concept that will replace this. What it is, I will not tell you now. It will depend on where I will arrive at the end of these lectures. I don't know at the moment. And so my plan is the following. My plan is to discuss very simple examples. Discuss very simple examples in a sequence. And each new example will have one more feature that will tell us a bit more about the final structure that we want. So basically, each lecture will have one new example, and we will build like this. And each time, the structure will be a bit more complicated or simpler, depending on your taste. And I will try to discuss only the simplest things. Now, I should say that as with groups, you could, everything we will discover here, you could do without. You could use the old framework, or even older. Nothing is necessary. It will just be at some point more convenient. So it's the same thing as you could say, I don't want to use groups. I'm fine with just linear algebra. Okay. and I already said that there would be no group and so on. And so just let me give you finally a little more, like we don't really want to throw everything out of the window. The thing that we will begin to realize is if we want to do symmetry in QFT, you see here there is absolutely no notion of locality. But in QFT, locality is absolutely essential. So our starting point will be, to these axioms, we kind of want to add locality. And the problem is, what does it mean? Add locality to this? Doesn't seem to mean much. But we will see that because of this locality, locality is a very geometric concept. Things happen at a place, and it should not influence on what happens at the other side of the universe. So this locality assumption will make the things more geometric and slowly evolve to topology. I haven't mentioned topology yet, but that's where topology comes from. Okay, so that's enough vague. I don't know if there are questions at this point. So vague that maybe there's no question. And okay, so then let's begin. As I said, each time I will introduce an example and try to discuss what are the symmetries, what is it that we want to call symmetries, and we will see that it will become richer and richer. In this first lecture, so today, I will discuss a free complex scalar field. And in the free complex scalar field, there is a U1 symmetry, which is the phase rotation. And I will introduce nothing new. So everything today will be what, in principle, everyone learns in a QFT or quantum mechanics lecture. It's just that I will begin to rephrase it. So I will actually not add anything. It will still be groups and so on. I will just use and describe groups in a way that maybe you are not so familiar with. But again, today, nothing new. Just the framework. Yes.
Can you remind us what the literature was when Bayer, Kapustin, Seiberg, and Willett wrote their paper, and like what motivated them?
Yeah, that's a good question. So I think they were where to start. So in 2 dimensions, there were already hints that symmetries could be extended with the algebra of line operators into these CFTs and so on. So there was this bit. There was all the supergravity and so on, which had extended charge operators and so on. And then in the month before, actually, there is also a paper, 1402 maybe, with just Kapustin and Seiberg, where they were. Oh yeah, there was also the whole. I didn't say that, but there is a whole aspect of this which aims at defining what QFT is, and in that line of thought, there was the TQFTs and how to couple a TQFT with a QFT, and gauging is an important point here. Like you have a TQFT with some symmetry and another QFT with a symmetry. If you gauge diagonally, then what does it give? And then they realized that this could be done with something a bit more general than just groups following the net procedure. This is the paper before. So I would say that was the line of thought. Yeah. But this is basically when I began doing. I was at the beginning of my PhD there, so I remember actually there was a conference in Paris, ENS, for I guess it was the 40th anniversary of the LPT, and I think it was in the okay, maybe in 15. But then Seiberg came and then gave a talk on this, and I remember that so I was a first-year PhD student, and I looked at this, and it looked very simple, and I remember thinking, why is this new? I thought this would be there forever, but apparently it was not. And of course, people disagreed. Yeah, that's a bit in line with what I said here with the groups. Some people, when they saw this, they say, yeah, we know this for 20 years. There's nothing new. And that's true. Everything can be done with that. Except if you have the right framework, we will go further. So that's a matter of taste, if you think it's new or not. I don't know if it answers the question. Um, so, so let's start with this very simple example. And from now on, everything I will say should be super precise and equations and so on. So now you should really ask questions if it's not clear, because the goal is to make things fit. Yeah, the other thing I felt when I saw these talks at the beginning, and even most talks or lectures that I see, I always have this weird feeling that, okay, the language that they use is very different from the one I learned in the QFT class. And I always felt like there is some cheating here. Why do we suddenly use these line operators or extended operators and so on? So I will try to motivate all of this and to construct them out of what we know from. So my goal is really to do this example here and to build the new language from what we know. So Noether theorem and so on. Okay. So let's do again. This is a very, very simple theory. Actually, I will even get so but then I will do computation. I want to write the action and so on here because to show you that it's insanely simple. But then you will see that none of the computations I will make really depend on this. So then at the end, I will tell you, everything I did was actually general. But this is kind of a trick. Okay, so let's write the simplest action. So we take a d-dimensional Euclidean space. So in order to not have complications, I will work in Euclidean. So you can think of weak rotation from Lorentzian. I will make then some comments about Lorentzian, but here let's do Euclidean because then I have simple. And then I take a Lagrangian, which is d mu phi, d mu phi. Right. That's my Lagrangian. Okay. The first thing I want to do, I hope it's okay, is to say, well, actually, I don't want to write this Lagrangian because it will be annoying to have all these indices around. So I'll just rephrase it, if you don't mind, with the forms language. So, d phi, so phi is my complex field, and d phi is just d mu phi x mu, so that's a one form. So the Lagrangian, I actually want to write as a d phi, dagger, wedge, star, d phi. Is it okay if I use this language, or is everyone happy with that? This is the Hodge star, but you should tell me now if it's not clear. I can write. This is just the same. It's just more convenient to do like this. Everyone is familiar with differential forms and the wedge product and the Hodge star. Good. So then you know that this is basically the same as this. This is a one form, and this is a d-1 form because of the Hodge star. So if you put this together, you get a d form. You can integrate a d form over the our manifold, and you get the action. So S is just the integral over M. So I will call M my manifold, and D. I'll try to put always the dimension of whatever object I have. I put the dimension as an index. Okay, so that's the action. And then there is the partition function, which is just the sum over all field phi of exponential to the minus s. So these are the things that I define. And then if I want to compute correlation functions in this theory, well, I can, I will compute path integral like that, but then with insertions of things. That's very simple. Now this theory has a U1 symmetry. The U1 symmetry takes the phi and rotates it with an angle. And then of course it rotates phi dagger in the other way. Okay, why is it a symmetry? Well, you can compute, sorry, here I should have written S of phi. So yeah, just to be clear, this of course depends on phi, this does not depend on phi because I've integrated phi. This will become important also later. So why is this a symmetry? Well, because, so when I write this, yeah, let's be clear. When I write this, phi is a function, it depends on x. Alpha is just a number. This is a transformation of the function. So to phi of x, I associate e to the alpha, phi of x, the same phase everywhere. So then this is just a number. And then clearly, if you compute s of this action, so this I will also call g. Not visible here. This I call g in U1. So f of g acting on phi is the same as f of phi. Okay. Here I put a dot. This is the action of g on phi. What is the action here? It's just multiplication. Okay. So that's how the symmetry appears. And now on z, I cannot say anything. I mean, z doesn't depend on phi, as you can see. So in order to describe what is the symmetry, I have to talk at the level of the action. At the level of the action, I say a symmetry is, well, in this case, again, I don't want to make a big definition. The definition will come at the end. What we observe is that here there is an action on the field such that the action is invariant. Okay. Now, what can we extract from the symmetry? Well, we know there is the Noether procedure. And so as you know, when you have a continuous symmetry like this one, Noether theorem tells us that it implies that there is a concept current. So let's review how this is done. So the symmetry here is continuous. And so we use this continuity to take a transformation which is very close to identity. So let's define a function v of x, which is very close to the identity. So being very close to the identity, it means it's e to the I lambda of x. So now I use lambda because lambda. So each time I will use lambda in all the lectures, this will always be a space-time or here space-dependent field. Okay, so I can write it this way. And I want this to be very close to identity, so I assume that this thing is very small. And also, I will assume that it goes to 0 at infinity. So I make a small transformation like that. This, of course, is not symmetry, right? Because it's not of this form here unless lambda is 0. So, but still, I take this this particular transformation and I compute S. I compute delta S, which is S of v of x. Right? Let me still write it this way. Okay, I compute the variation. Now the question is this variation 0? Well, because of this, there's no reason why this should be 0, because now this is varying. So as you know, this will mess up with the derivative and so on. So there's no reason for this to be 0. But if we are on shell, so if we are at a solution of the equation of motion that I didn't write here, I could have written, yeah, write it here, the equations of motion. They are, as you know, the free wave equation. equals 0. If I write it in this language, it's d phi 0. So if but we can also forget about this. If we have a solution of the equation of motion, then by the action principle, we are at the extremum of the action. So any small variation should vanish at first order. So actually, if we are on shell, we have that this variation should be 0. It's not because of symmetry, it's because it's a stationary point of the action. And now, well, now you can compute this, expand it at first order. So you just plug it in here. You plug it in here. So it's integral over m of g. And now, because it's very small, you can say that this is 1 plus I lambda and so on. I will not write all of this. I lambda, I dagger, wedge, minus the other thing. I don't copy it again. You take this, you expand to first order in lambda. And then what you get is, write the signs right. You get I, m of d lambda. So yeah, there are some d lambda, wedge something. That's the first order. There's nothing that depends on lambda without derivative because this goes away, and there is something in d lambda. And the thing that is here, I call it, by definition, star j. So in this case, what is star j? It's just, and let's compute. J is minus pi dagger star pi. Like that you could compute from the Noether procedure. But it's really, this is just the computation. If you don't know about Noether, you just do this, you compute that. And now this you can integrate by parts. Use the fact that lambda is 0 at infinity, then you get minus I of m of lambda with star j. And so if you are on shell, this should be 0. This thing doesn't depend on lambda. This should be true for any small lambda. Therefore, that thing should be 0. So from here, we obtain that on shell. We have this conservation law, which is the Noether theorem. So we have rederived Noether theorem. Up to now, nothing new. That's the standard textbook. Any question on that? So let me now do something which is a bit annoying. I will add, I promise that I will put dimension of things as an index, just to be clear, and then maybe I don't do it right now. Okay, I will not do it right now because it will clutter. But what I wanted to do is to start putting little 0 here, little 1 here, to say what is a 1 form, what is a 0 form, and so on. Maybe I will do it just from lecture 2. No. But we should remember that this J is a 1 form, as manifest by his equation. This is a 1 form, so it should be wedged to star over 1, as you can see also from here. Okay. Conserved curve. So this is the conserved. Okay. Now comes our first thing, which is slightly not always done, say in the standard treatment. So we can use this current. Okay, maybe I write on the other board the long statement. So we use this to couple the theory to a background gauge field. This I will write many, many times, so I will call it BGF. So this guy is the key player of all this series. This and there are two, there's the dual aspect. So what does it mean? It means we can define, so I will try to be precise here. So we define a new theory how to define a theory? Well, using an action and a path integral and so on. The new theory will have an action S, which now depends on two things, phi, our original guy, and B. Okay, maybe now I start putting actually the indices. So phi, I put a 0 to say it's a scalar field. It's a 0 form. B will be a 1 form in this case. Why is it a 1 form? Because we use the Nutter current, which is also a 1 form. Yeah. So how do I do this? Well, so this is the definition. I take the former action, and then I add minus I integral over M of B1 . Okay, so it's still my free theory, but now I have two fields. I have a scalar field and a one-form field, and the action is the former one plus this added term. To construct this term, I use all this procedure here. This procedure outputs a star J here, and now I couple to a new field like that. But this is my new theory. It has a partition function, which is Z. And now the partition function, very importantly, depends on this field B. This field B is not summed over in the partition function. So the partition function is very similar to the previous one. It's just that there is now this guy. And now, this new theory, we can observe that it has, we can ask the same question as before, what kind of symmetry does it have? And now, this new theory, a nice feature is that it has a huge symmetry. So the new theory has a symmetry. What is the symmetry? It's the symmetry of all maps from M to U1. So now it's not just U1, it's all maps. So it's a U1 dependent field. So this is the group. And how does this act? If I have a lambda, well, e to the I lambda of x in here, how does it act? Well, it transforms phi to e to the I lambda, I, and it transforms b to b plus d lambda. So that's our new theory. It's a different one. Very different theory. It has a very different symmetry and so on. But we built it from the previous one. This huge symmetry here, this is called a gauge symmetry. The gauge symmetry, and we will see the reason for this name a bit later. And B is the gauge field. But because B is not summed over, it's a background gauge field, BGF. So very important. It's a background gauge field, not summed over. It's really a symmetry. It's not at all like in the standard model or something where there is no gauge symmetry. There is just some redundancy. But then, of course, we could try to gauge it if we wanted to. Gauging it, we would like to, we'll see how to gauge things. In principle, if you're naive, you would say, good, I have another field. Why don't I just integrate over all the beads as well? Then if you integrate over all the beads, because of this huge symmetry, the result will be strongly infinite because you can shift B by anything like that. So when you gauge, what you do is you say, oh, there is a gauge symmetry. So then you take, then you take one element per orbit here, and you sum only over the orbits. That's how you would gauge. But we will be much more precise a bit later. Yes.
Sorry, maybe I missed this, but because you said several times that this is not at all what we have in the standard model. But then when you actually, and I understand this, but like well, when you have a proper gauge symmetry as you define it, then it's always background. Like the gauge field, is it always going to be background or?
Yes.
It's always background field.
Yes.
Okay. Nice.
That's yeah. So that's why usually there is kind of a dispute. Like people say, oh, there's no gauge symmetry, it's only gauge redundancy. No, there is sometimes gauge symmetry, but then the gauge field is background.
Okay, thanks.
Okay, so we have this.
Are you going to integrate at some point over the B with the log of some? Are you using, for example, log of Z as the action for the B?
Yeah, the effective action. Yeah.
For the B. Because up to now the B field is not integrated.
Yeah, sure. I will. We will discuss gauging and so on. That will be part of the. This will be next time. Now we were just. At some point we would want to gauge and so on. But first I want to. I will not gauge today. I want to arrive at the new language first. But this will use that. Okay.
So maybe just another comment. So the symmetry is like connecting different partition functions with different external fields.
Right, exactly. So if the partition function depends on fields, then of course when you say something has symmetry, then it means that the partition function is invariant under that symmetry. That might be what you want to define as symmetry. I still haven't defined what symmetry is, but yeah, that will be part of the requirements. But you see, that's why I contrasted with the thing before. My initial theory had a partition function which is just a number. So how do I define symmetry there if I don't have fields? So that's the point, actually. The point is that we will always be able to do this, and then we will always consider that thing and talk about symmetries there. But there will be some more reformulation before. Okay, let's just check that this thing here is a symmetry. It's a very trivial computation. We compute delta lambda x of this new action. Okay, I call it S again, but you understand it's a new one. If it depends on two things, it's a new one. Well, let's vary with respect to lambda x. Formally, up here, I have computed delta x, delta f of the first term, so it's this term here. So it's minus I integral d lambda wedge j. That's the result for the variation of this. And then I have the variation of this. And the variation of this gives the opposite sign, plus I b. So I vary b, and b gives 0. And 0. So that's 0. So yes, this is a symmetry. It was done in such a way that it is. So that's why this is a completely general way of building a huge symmetry. And then let's just check how it works at the level of the partition function. So at the level of z, so if I take z of b1 and I shift with this, I put a new z. How does it work here? write the partition function. So that's integral over d5. And then we have exponential of minus s, phi 0, and then b1 plus d lambda 0. Okay. We want to relate it to z of t. So then we have this term here. The idea is to use the invariance of the action, we just proved here. So here we do a change of variable in the measure. So I define g of x to be exponential of I lambda of x. And now I integrate, so I change variable locally. So I have v of g of x, I adjust by g5. So this is just a change of the value variables. Now I have g of phi here. And the same thing here. And now I can do two things. I can use the symmetry of the action. So that thing is the same as if I remove g and lambda. And then I can also assume that the measure is invariant, that g of phi is actually the same as d of phi. I will then comment on this assumption. So if I assume these two things, then I'm down with g phi and e to the minus s I d1. And that's just z. So I have shown that z is indeed invariant under this transformation. So here there are two things that were used. Important. So from here to here, there is the symmetry. Here, and from here to here, there is the invariance of the measure. In more general context, you could imagine that maybe the symmetry will not be exactly that. Maybe it will produce some additional term here. For instance, if we had a counter term, I could have added things here that don't depend on phi at all. I could have added maybe a b wedge star b or stuff like that, which then would have produced other terms. So here maybe I picked a different thing. I would have gotten other terms. Maybe here also I get some Jacobian factor from the change of variable. So all these things, they can happen. So if I have them, then I would not have just this result, but this times some other thing, z, that depends on d and lambda, z anomaly. So that term would appear if I had a problem in one of these two transformations. In the particular case I'm looking at now, the free scalar, there is none. This is this I've proved. And this thing, well, you could expand in the basis of oscillators and so on. And I don't want to discuss that thing. It's just not there. So in our case here, there is no such anomaly. But that's where the anomaly would appear if there was one. If that was here, it would not mean that the theory has no symmetry. The symmetry is here, and is here to stay. It's just that at the level of the partition function, it would act in a. The partition function would not be strictly invariant, but would be invariant up to some factor that we would need to count. So I will come back to this also later. It's just a comment because you might be worried about. Okay, so let me just write the conclusion of this. The conclusion of all this is that, and this is in a way this is a reformulation of the Noether theorem. If the theory has a U1 non-anomalous. So here I put this qualification because it's the fact that this thing is absent. So it has a U1 non-anomalous symmetry. Then it can be coupled to a background gauge field, thus defining a new theory with gauge symmetry. And this gauge symmetry is, in my case here, the equation that's the conclusion. This would be the way to state Noether theorem. Let's call this statement. This is statement number 1. Are there any questions on that part? Okay, this is I promise that there will be nothing new today.
Again,
Yeah.
the symmetry part where you said if there's more term in the action, you need counter terms such that variant under this transformation.
Yeah, so you could have indeed more terms. Maybe there well here. Okay, the way I present it here, the definition of this is completely unambiguous because this J was computed in a very there is an unambiguous way of computing J and then coupling it this way. But indeed you could, from another perspective, have arrived at an equivalent version of that theory with some counter terms, and then maybe the action here would not be invariant. But then, if it's just this, then you could redefine fields or add counter terms such that it is actually invariant. The point of the anomaly is if it is not possible to do this with any redefinition of the field, any addition of counter terms, if there is no way to get rid of a phase here when you do that, then you would say there is an anomaly. That's the definition. But again, I will be more on this.
The anomaly appears either the invariance of measure breaks down or the
Yeah. Yeah, exactly. So sometimes, yeah. I'm not the biggest expert of anomalies, so I'm a bit ashamed of making those statements. But let me quote Seiberg, who said, "Okay, anomaly is probably the topic in theoretical physics which has been the most misunderstood, and there are layers and layers of miscomprehension of what anomaly is." And so depending on the years, every decade, there is a new thing, and then they're all wrong by a little amount. So there was a point where anomaly was believed to be due to the non-invariance of the measure, maybe for the fermions in particular, that this is really due to the infinite dimensionality of the Hilbert space in quantum field theory. Okay, I don't remember all what he cites. So none of these things are really essential to the anomaly. So you could have anomalies. Actually, we will see one in quantum mechanics. So finite dimensional Hilbert space, no fermions, nothing, and still have anomalies. It's yeah. And actually understanding this is I promised at the beginning that anomaly was a murky concept. Part of the goal is to make this very clear. So I don't know if I answered the question. Yes.
I understand this is to be pedagogical, but because we're going to talk about QFTs, and Noether theorem is only for on-shell conditions.
Yes. Yeah. So I said on shell. On shell, we have the concept current.
QFT we can talk about. I guess it's a stringized energy. Does everything hold there? Just
Oh, you mean a consequence of the
suppose I don't false on-shell condition.
Mm-hmm.
Then can I still use that? Because here explicitly we impose on-shell condition to begin with.
Well, no, I don't impose. I said to find the Noether current, to prove Noether theorem, I used it at one point. I said the variation that I wrote is equal to 0, and that's it. But then I immediately, I'm not using that anywhere. I'm just using it at one point to say that the current is conserved on shell. Otherwise, so now, if there is no more question, I will translate again. So we moved from our very familiar statement of symmetry with Noether's theorem to this thing here, which is summarized here. And now I will move one step further and use this in a geometric way. And that's the introduction of symmetry defects. So the goal is to, if you geometrize the statement here. Because, so in principle, everything could be done with this background field and so on, but at some point it will be, there will be many fields and so on. So it would be much more convenient to have a graphical way of handling all these equations. And this is what the symmetry defect calculus gives. So let's do it here. So we pick sigma b minus 1. This will be a closed oriented submanifold of dimension d minus 1. I put a dimension here. And, let's pick alpha, real number. These are my two ingredients. And out of this, I can I define a particular function lambda. The function lambda is alpha times theta of sigma. What is theta? Theta is a Heaviside function. So it's a function that, so if you imagine that you are in one dimension, then sigma is a point. There's a point here, and then that thing would just be a theta function. If you're in a higher dimension, what does it mean? It means because I have a closed oriented submanifold, I will also assume that well, here my base manifolds are B anyway, but I will assume that this sigma, let me be a bit more precise. So here we first do a local analysis. Point number A, local. I do locally. So locally, my closed submanifold separates M into two parts. So there is M, this, and then there is sigma. And then it separates M into two parts. Let's call it M left and M right, like this. And then what is this theta function? It's a function that is 0 on this side and 1 on this side. Okay. So of course it's a distribution. It's a non-smooth function. If you're worried by that, well, just take a good approximation of theta, which is smooth. Okay. Now, so I want to apply now this statement with that particular function. So if I compute z of v1 plus z, what do I find? I'll just plug it in. E to the minus s of 5 could have written. Do you make a break or what's the rule?
The people, I don't know. Who wants a break right at the end?
There is a
10 minutes, 5 minutes.
okay. We can just maybe let me do this and then we do 5-minute breaks after. I just finished. So So what is the impact of this d lambda, which is here? Well, I erased the action, but you remember there was an I, there's an alpha that comes from here, and then there is this term, which was the b, but b is now is this d lambda, so d lambda 0 with star j. That's what the partition function becomes. And now let's look at this term here, and then we do a little bit of computation here. This thing is the integral of theta, of d theta, wedge star j, but that's the same as what d theta is a delta function. So delta 1. And now what is the, by definition, when you have a delta function, it's a delta of the manifold of sigma, and then that reduces to just an integration over sigma d minus 1 of star j. Of course, the dimensionality works. This is a d minus 1 form. It can be integrated over the d minus 1 dimensional manifold sigma. So that's for the exponent here, which means that thing is just, okay, let me write now this equation as a correlator. So, okay, each time I will write, if I write something in brackets, and here I have to put which background gauge field I'm using. If I do this, this means for me the integral of over g phi e to the minus s of whatever I don't normalize, or if you want, you can normalize everywhere. Right? This is my notation. Now, with this notation, what does this equation mean? Well, on the left-hand side, I have the wave of nothing in the background field, which is d1 plus d lambda. And on the right-hand side, I have an expectation value of something with just the d1 background. But then what do I have? I have an e to the I alpha times this. So this thing is an operator that is reported on sigma. And this operator I call u g of sigma. And ug of sigma, by definition, is just what is written here. So ug sigma is just e to the I alpha integral star j 1. Okay, that's what we have. And that guy here is, I didn't review it, but that, as you know, is the charge over the d minus 1 dimensional manifold. So in the Noether theorem, you have the Noether current, and then if you integrate the Noether current over a d minus 1 dimensional slice, you can think of it as a time slice, then you have just the charge at a given time. And then if you exponentiate the charge, then you have this operator ug. And then what we see is that taking an average of nothing in the background shifted by d lambda is the same as not shifted and having this. So in the end, you see that performing background gauge transformation like this, if you have a particular kind of lambdas, is the same as making such a thing appear. It's much more convenient to work with this kind of pictures rather than this. So after the break, I will move and translate then everything about symmetries into the language of manipulating this subbases and so on. So maybe we have the 5-minute break now.
Yeah, maybe 10 minutes, but exactly.
Okay,
So it means come back after 5 minutes, please.
Yeah, so during the break, someone pointed out I forgot an alpha here, so I can move it. And another question I had is, what are we doing exactly here? So just to be clear, we said that this is, if we have a symmetry, then we have this for every function lambda. And then as a consequence, I said, let's pick a particular function lambda here, and let's see what are the consequences. So what I'm doing here is a consequence of this, the implication. So what is the consequence here? Is that if symmetry, then we have this, and then we can trade sometimes certain forms of background page fields to we will remove them, but instead we have now this surface operator or hypersurface operator. So this is the consequence. Let's just see, in order to understand exactly what this thing is doing, let's repeat the computation to answer another question I got. Let's repeat this computation here with some operator insertions now. So this will be trivial. Now let's put some operators. So let's say I want to compute a correlation function. Okay, again, think of this free series. So it's very, very trivial. Let's put some phi. Let's put phi. But you see, as I said, not much of what I say depends on the theory. Except, yeah, also Sylvain asked a question in what I just erased. There was the variation of the, when I checked that the background gauge symmetry is a symmetry. It could be that there are terms that depend on the variation of the J, and I'm not sure what's happening, so I will check for next time. But here, let's repeat that computation, still in the free theory, with some operator insertion. So let's put phi of xl and phi of x right. You could put any number of them, but okay, let's just put 2. So xl is a point on the left part. I put a point here, xl. I put a point here. And I want to repeat that computation here. Well, it's very simple, actually, similar to what I erased. Remember when I checked that the transformation is a symmetry, I made this change of the variable at some point. Well, we can just do it here. So what it is, this is not defined. So this in the background, this background here, d lambda is integral minus s, and then I don't put always the superscripts. Now here I have from the background I have the insertion of this operator u, and then I still have my insertions from here. Okay, so here I just done this, and now now what do I want to do? I want to do the change of variable. Now I define again g of x is, I define again g of x equals e to the I lambda of x. So what is this e to the I lambda? It means, due to the form of lambda, it means g acts trivially here, but it acts with the phase alpha on this side. But okay, let's first do the general thing. So now I integrate over g phi. Here is the same computation as before. So this is just a change of variables. So here I have g phi. But now I can plug this operator insertion back into here. So that this becomes b plus d lambda. And then I just have the, here I have now g phi on the left and g phi on the right. This. And now I do as before, I use the invariance of the measure, invariance of the action under the symmetry. And so this becomes just g phi, this becomes g phi is minus s of phi b. But now lambda is gone, and here I still have this. And now, as I said, G is identity on the left, so it's just phi of x left, but on the right, it's e to the I alpha. So you see now I have an equality of correlators in the same background D, one coming from here and one coming from here. So let me write this here. So I have that, now I have my operator here, UG, and here I have the points, I have phi xl, and here I have phi x right, in the background D, that you could take to be 0 if you want, but it's just the general one, is the same as, well, what we have here. So now there is C phi of xl, and now there is G phi of x right, and nothing in between. So what this shows, so that's the, what this shows is the insertion of an operator UG somewhere. That's why it was important that oriented. You know, I have to pick an orientation. So there was an orientation in this theta, so it acts on the right. Everything is local at the moment. So locally, whenever you insert a UG, it means it's the same as transforming everything on the right with an action of G and doing nothing on the left. So it is in this way that these operators, they geometrize symmetry transformation. So this is the quite fundamental equation. That's the reason why these operators can implement. Let's just mention another property. I could have said it before, but another property of the, what time does it end? Then that's 15 or?
No later than 4:30.
Okay, let's just do it. Yeah, so one thing I should have said, maybe I can, let's sit here. Another very important point about these operators is that this operator UG is topological. What does this mean? Well, it means if I take two sigmas, but one of them is here, and the other one is there's a little bump here. So there is, say, sigma 1 and sigma 2. Then what I say is that these operators, provided there is no insertion in between, they will give exactly the same results once we put them in the partition function. And what you can check as an exercise, it's very easy to check that if you have a small deformation like this, there is some d-dimensional manifold in between, and this is ND, and then you can check very easily that the integral of star j on sigma 1 minus star j on sigma 2 using Stokes' theorem, it's the integral of d star j on the middle thing, and then once you put this in the partition in the correlation function, you use the fact that the current is conserved, so that this is 0, and so the operators UG of sigma 1 is equal to UG of sigma 2 in the partition function. So when I write this, yeah, there are always different things, and it's linked to the on-shell or off-shell question. When I write this, I don't mean that these are the same operator. They are obviously supported at different points. I mean doing this. And many equations will always be, this is what I will mean when I will drop the correlation. So this is what we mean by topological. Okay, that's another property. And then a final property that we could check, making a very similar computation, is that, so here, I erased, but the background gauge field that I used to go from nothing to having the surface was to involve this lambda, which was, well, which was equal to alpha times theta, sigma. So that's a, if you want, that's a large gauge transformation because you see it's a step, so it doesn't go to 0 at infinity. But then there are small gauge transformations. Again, it's not too important to have this vocabulary now, but if I want to move the position of those things, so this is what it's doing here, then you use a small gauge transformation. You use a lambda, so you shift lambda by some other quantity, like a theta minus theta. So you have a function like this. And that moves the operator from here to here. So using these lambdas, which decay at infinity, you can move things around. So this is what implements this topology. And then using a very similar thing, now you use a lambda 1 and a lambda 2 with two different alphas, you can very easily check that these satisfy a fusion rule, UG of sigma e minus 1 times UG of sigma e minus 1 is equal to UG prime, UGG prime. What do I mean by this? It's again the same, so I don't write it, but it's within correlation function. You have this. And then what I mean by here and here, you should imagine that these two, maybe I should twiddle here, so that these are slightly apart, so that this makes sense to consider these two. And then the point is you can find a background gauge transformation that brings that guy close. So here you have UG, and here you have UG prime. And then this is the same as UGG prime. Provided again, there is nothing in between. If there was some operator in between, you can read from this equation, one of them would, when it crosses it, would act with the symmetry on the operator. Okay, so we have those things. So now I can write the conclusion. Maybe I write it here. I have the other conclusion already. So the other conclusion is if a theory has a U1 on an anomalous symmetry, then this was first consequence, then second consequence, there are topological operators supported on codimension 1 manifolds, closed manifolds. Satisfying, so implementing the symmetry and satisfying fusion given by the group law. So that's second consequence. We have proven here. Yeah, I just use this to build it. So it's clear that this implies. So if there is symmetry, then there is this, and then there's this. Again, at the moment, I have not done something general. I've just talked about the three complex scalars, illustrated everything from this sigma. Now, up to now, I've been only, oh, I erased it, but I wrote at some point that I was doing things locally. I was assuming that sigma was dividing space into two parts and so on. So, what to complain about this? Well, in my example where I said I'm on RD, it's clearly possible. But then, as in the code at the beginning, you can draw a donut, and then things will not be so easy. Like what if I draw a donut? So if this now is my manifold, baseline manifold, and then so this is 2D equal to 2. Now these topological operators are supported on lines. So for instance, something like this. Now clearly that line does not divide the manifold into M left and M right because they're the same. So that's where the global story starts. So whatever I've written, I just erased the fact that when the operator is moved, then it acts with the symmetry transformation. This is all true. But now I cannot now define my lambda function. I cannot find a lambda which will create that. Which means that this configuration is not related to one without it by any lambda. And they are in different topological sectors. So that's just one comment about the global aspect. We will come back a lot on this later. But so that one, just to mention, this is not created from the empty donut by adding the sub-V line. And here you can begin to see a cohomological flavor of this. You see, the B, basically what this equality tells us is that the relevant information of B is entirely contained in B up to adding d lambda. The thing is, B here is not supposed to be closed. So I said nothing about dB. But we will see now that for a lot of cases, dB is actually closed. When are those things? Well, for everything that comes from a, let me say it this way. So, so any network of topological defects what do I mean by network of topological defects? I mean, take a lot of sigmas, and then okay, maybe they merge at some point, but we will see exactly what's happening there. But okay, an example of merging would be, okay, so here I try to draw in 2 dimensions, so 3 total. Now let me draw 2 total, and so now these sigmas are lines. So this equation I can also fuse only partially, so I could draw it as something like that. Where here I will have G, and here we'll have G prime, and here I will have G prime. This kind of thing is allowed. See, I make a transformation. This locally can still be obtained from a particular lambda. We construct exactly as before. And okay, any network like this, which means yes, I have a network. Imagine this in higher dimension, but okay, this is in 2 dimensions. So each line is labeled by a G. And okay, you should define an order so that if you put an orientation, I said at the beginning that they were oriented. So there is a UG, and then there is G1, here there is G2, and here there is G3, and at each triple intersection, the product of the G's is 0 to satisfy the fusion law. That's equivalent. So a network of topological defects of that kind always realizes a flat background B1. B equals 0. This is clear. So first of all, okay, what does flat mean? The intuition is a flat one form. So one form is a connection. So it's something that you can integrate over a line. And so if you have a one form, you can start from the point, integrate B over a line, and then you get something. The fact that it's flat means the value of the integral, which is holonomic, does not depend on the path. So this or this path give the same value. That's what flat means. That's the intuition. Now, in equation, it means dB is 0. From what I've said here, it's very clear that it is flat, because whenever you move from one cell to another one, you just, I erased it, but you just, it's here, you get acted on by G. It's equivalent, right? Having UG is equivalent to not having it, but then being acted on by G. So any network gives rise to a flat B field. And we also just said that the B fields are defined up to exact terms. If I add a d lambda, then I get the same. Which means the topologically, like the really distinct configurations of D fields that I can get out of networks of lines are in the cohomology of in the first cohomology group. I will write it more clearly. So yeah, field, and so B here, the class of B, so it means B up to the addition of d lambda 0 belongs to the first cohomology group of your space-time manifolds into, in this case, U1. U1 is, because U1 is our symmetry group, it is what P takes values in. And so if here, clearly I can restrict this number one statement here to flat if I want to. Clearly, if I have a symmetry, I can couple it to a flat B field. And then if I do this, so if I add flat, it's clearly still true because it's weaker. It clearly still implies that because the lambdas I used to go from here to here were flat. And now I can go the other way, because if they are topological operators, I can put as many as I want, and then I can realize any flat field. This I haven't really proven, but intuitively it's clear. If the group is continuous, you might need an infinite number of them, so it's a bit murky. But we will see just in a few minutes a discrete example where the group will be Z2, so that will be clearer. So, but let's admit that these two things are equivalent. Is it clear what these networks are? It's a simple generalization of just having one defect on the one submanifold, except now we can have junctions, and we impose that at every junction we have like that. I will say more about them in a minute. But let me write the conclusion of this argument. I mean, the conclusion will be actually our definition of a symmetry. So the definition is, we say that a theory. So let's take let G be an abelian group. Not so important that group is abelian, but let's take abelian group. Then we say that a theory has symmetry G if, well, either this first or second segment, well, and of course you should replace wherever you see U1, but you don't see U1. But that's not my definition. So we say that the theory has a symmetry G if either you can couple it to background gauge field in such a way that or equivalently to flat background gauge field, or equivalently if they are in the theory topological operators which are supported in closed manifolds, and well, that's kind of trivial, and which satisfy the fusion group law. If you have this, then you will say that there is asymmetry G. And the point of that symmetry is that this works also for G discrete. Right? If G is a discrete group, the derivation that I gave here doesn't work. There is no Noether current. There is no so I have no way to prove this fact from the Noether procedure or anything. But I'm not doing this. I'm defining. Having a symmetry is now this thing. Is to be able to find these topological operators. And that's what this is the slogan that is sometimes said, that symmetry is topology, because we focus on the second point here. If you have things which fuse according to the group law, then you say that group is a symmetry. And I want to just illustrate this with a very simple, very simple. I just also give a reference and write a bit more precisely the axioms from here. The axioms for these networks, if you want to read them, they are given in a paper by Thorngren and Wang. In this paper, you can read what exactly are the axioms that you need to make this definition very precise. I will just write them as the drawings. So as drawing, what do you require? You require that you take any kind of network and you first make it into what they call a G-foam. So G-foam is just, you don't want to have too many things joining at a point. That would be too messy. So whenever you have this, you know, as when you have foam, they separate the bubbles, and every junction is a triple junction like this. So the only networks that you allow are these G-foams, but they meet at 3 points. This is if you are in 2D. So if you are in 3D, they will meet. 4 will meet. If you are in more dimensions, more can meet. Then you should have this law. So you just write the 4 axioms. There are 5 axioms, numbers 0 to 4. So if you have G1, G2, G3, I already said that G1, G2, G3 should be identity. Then the other axiom should be that whenever you have G, when I write G for UG, if you have G and then you have some operator O here, this is the same as G acting on O, G on the other side. So that's the equation that we erase now, but when you pass the operator path, it acts on O. And then there are some very trivial axioms that you can, when you have a G, it's the same as deforming it a bit. That's the topological assumption. Then there is another axiom, which is when you have nothing, it's the same as making a G appear. The loop. So out of this bubble, here I could have put some bubble like this, doesn't cost anything. All these equations are true within correlation functions. And then the last axiom is that whenever there is a triple junction which is like this, it is the same as when if you recombine it this way. You will have 1, 2, 3, 4, 1, 2, 3, 4. And so which means if your foam is like this, then you can recombine kind of crossing equation.
Why is it an axiom and not the consequence of the other one?
Of which one?
Of the one.
This one here? It's not an. It's okay. What is the good question? So of course, if what is the consequence of that is that locally here you will have 3, 4, which is the same as 1, 2, the inverse of 1, 2, and here you will have here 3. That's for sure. What is not the consequence is that there is not a phase when you form from one to the other. This is really a topological manipulation. It's not. It's a non-trivial topological. Actually, there is no. If you try to prove this from the computation that I made with the partial function, you will see that having this is actually equivalent to having no anomaly in the. So actually, this was my next comment, but it's good that you asked. All these axioms look a bit trivial. The only one which is a bit tricky is actually this one. This one will be modified if there is an anomaly. So typically, there could be a phase here that appears, and we will see that in detail next time. There can be a phase, and then that is the anomaly. Which means the anomaly can appear in extremely simple setup. Actually, we will try to have the simplest of all. Like you could take the group to be Z2, and just a few, like some free fields and so on. But if you manage to have that this is equal to, say, minus this, then that would be an anomaly already. Okay. Are there more questions? Yes.
So I can't understand what the meaning of the arrows is. Sometimes you put arrows, sometimes there are not arrows.
Yeah, so there should be, here I didn't even write it here. Those oriented, I mean, I wrote it at the beginning, but they should be oriented in the way that I generated them because they act on one side. It should say which. Yeah. Locally, they should be oriented, and if really it's one manifold, then it should be oriented all the way. If it's a network like this, well, you should just keep the orientation on each thing. Then, of course, for this vertex, now one arrow will go out, one will go in, and then you put an inverse. You put appropriate powers.
Do you mean there's a zero flux condition at each vertex?
Yes. Yes, you cannot. Yeah. That's exactly the statement of this madness. Okay. So now we have it. All these comments were to arrive at this definition. So we've done nothing new. We've just taken a group and we have said what it means for a theory to have a symmetry group G. And the point is that this definition looks a bit, not weird, but it looks a bit too specific. You see, it is the one here. First of all, we have this thing, codimension 1. It's weird to have this specification. There is this closeness. This is what imposed the background here to be flat, but what imposes that. And then we have a very specific condition here that the fusion should be group law. And this is strong. If you know anything about fusion in general, you could have more general things. So the whole point of the generalized symmetry is to say, okay, if this is the definition of what a group symmetry is, symmetry is simpler than that. To define what is a symmetry in general, we just drop all these weird assumptions. So we will come to that later, but we will see in the next examples how one after the other we will drop these assumptions and arrive at a much simpler and also more general notion of symmetry. Before that, again, I said today, which there is nothing new, so I will be true. I want to illustrate with a extremely simple lattice, an example, Z2 symmetry. To have an example of a discrete one on the lattice. So I will take now, also this framework is more general than QFT. Yeah, everything I say, I said it at the beginning. There is Euclidean and Lorentzian. You can go from one to the other. I should say here. So if you, the reason why I picked a Euclidean at the beginning is because the discussion is a bit simpler. Everything are these topological operators or defects. This is the same thing. When we will move to Lorentzian, then there is a difference whether the operator is supported on a time slide, in that case it's an operator, or if it has some time-like directions, because then it will be a defect in the, so it will define twisted Hilbert spaces. And the fact that these two things should be compatible with each other, if you have relativistic invariance, imposes very strong constraints on symmetries. And so we will see examples of that. But yeah, so there is the correspondence Lorentzian Euclidean. There is always the possibility to discretize. So whatever is valid in the continuum should also be valid on the lattice and conversely. So it's nice to be able to jump between one and the other. And there is the correspondence between quantum models in d dimensions and statistical mechanics systems in one more dimensions, which is also used and related to all of this. So we can navigate between all of these frameworks. So here, again, I will all of these words to take the most boring and easy system of all. Let's say that I have a lattice, a d-dimensional lattice. Let's take ZD. And then we put a spin on each side. There is a sigma I, which is plus or minus 1 on each side. And we take the energy H, which depends on the spin configurations, which is just this. Why not? So Ising model without transverse field. Could add it, but let's just do that. That's the simplest. Now, as everyone knows, there is a Z2 symmetry that flips sigma I to minus sigma I. But you should do this globally. So that's the equivalent to what I said at the beginning. It's a global transformation. To flip it only on one side, that's not a symmetry. Okay, so that's the Z2 symmetry. And now everything we said can be done. So let me just say, so the symmetry can be characterized in three equivalent ways. Number one is we can include codem UG. So here G, Z2 has just two elements, only one is non-trivial. So I just denoted by U, is the one associated with the non-trivial element. So we can include U of sigma d minus 1 operators. Yeah, I don't rewrite the whole thing, but that's basically this sentence. That's one way of characterizing the symmetry. Another way is we can couple to background gauge field. So let's do that. And a third way, which we will see is equivalent, is we modify the Hamiltonian, which is adding a defect. So let's just check in this particular example, again, very simple, how it works. So a closed space. Okay, so that will be my this will be sigma. Now, what is U sigma? It's exponential of minus minus 2 beta j times the sum over the links belonging to the sigma of sigma I sigma j. So that's the operator. So how do I know it's this? Well, I could derive it, but I'm just derive it by checking that the same computation as what we did before work. Very trivial thing. If I compute the expectation value of sigma, is the sum over all spin configurations of e to the minus beta h times the thing here, e to the minus 2 beta j sum sigma j. And then, well, it just recombines minus beta j and now, so there are some sites where sigma crosses, some links, sorry, that sigma crosses. Sigma is codimension 1, so they cross links. So some links are crossed, some links are not crossed. If they are not crossed, then we just have the contribution from h, which is 1. If they are crossed, then we have a minus 2, so it becomes minus 1. So we just have minus 1 to whether or not the link belongs to sigma. And sigma I sigma j. So that's just the expectation value here. And now you recognize here, I hope you see the parallel between this and the computation in the QFT before. That's when I had the U, it's supposed to be exactly when I had the background gauge fields, the d lambda, which was the, and which was giving this is the equivalent of the U, which was the integral of the sigma of the star j and so on. So I should then use we can just say that this is the sum of the sigma of e to the minus beta h sigma. So here I have modified my Hamiltonian, and the modified Hamiltonian can be defined by h modified of sigma is the sum over ij of that thing here. So that thing I will call it d, dij, I, sigma j. And in order to be very clear about what are forms and so on, the interpretation B should be a 1 form, sigma should be a 0 form. Why is that? B has 2 indices, sigma has 1 indices. Well, that's because with lattice we are looking at forms, and a P form on the lattice will have P plus 1 indices. Why is that? Because I have to say exactly what are these forms. This is the way the homology of forms are computed. Since so just a reminder that this is important because we will use it in the title. There is topology, so I should make some reminders of topology, of cohomology actually. So, and that's why I do it first on the lattice, and then I will say that it's the same in the continuum. So if you're on the lattice, then there are points, there are lines, there are faces, there are volumes, and so on. Let me write everything as triangles. Even if the lattice is not only triangles, I can always pretend it is. I add lengths and then it's fully triangulated. So, and And then I can define the nth cochain, defined on whatever lattice. So let's say that x, so on x with coefficients in G. So I pick a group, abelian group G, and X is some space. I'm a bit vague what is space, but it could be a manifold, it could be a lattice, it could be something exotic, and that's an abelian group. And then the nth group of cochains on X with coefficients in G. This is just the set of all functions defined on n-dimensional simplices. N-dimensional simplices. Simplices are those things. 2D. Okay, so you associate an element of G to every n. And then there is a boundary map, delta, which goes from Cn to Cn plus 1. G. What's the boundary? Well, it takes, let's say that phi is in Cn, so phi is an n chain. So it associates a group element to each n-dimensional simplicity. Let's take a one chain, or let's take a one chain here. Then what is delta? The delta of phi, it's an n plus 1 chain. What is its value? Well, if you want to evaluate it, let's say phi is a one chain, then delta phi is a value on the two chain. It should associate an element to everything. And what is it? Well, it's the sum over the edges. So in formula, if I want to write this, okay, let me write it this way. So sigma, let me write it in a symbolic way. Let me write it for two-dimensional thing. Is the sum over I are all the edges of -1 to the I times I don't know if it's not clear, then maybe next time I will be a bit more precise, but delta is just this. Then you can check, it's very easy to check that delta square is 0. Delta square is 0, and so the n cohomology G is just the kernel of delta divided by the image of delta, so it's the closed forms modulo the exact forms. Except now we are not in differential forms. We are we can be defined on anything. It doesn't need to be smooth, and we are valued in anything. Doesn't need to be something smooth either. Here, G could be G. So now we can just check that indeed one form or one cochain is something which is valued on one-dimensional links. But in the lattice, where the sites are labeled by I, then the links are labeled by two indices. So that's why one form will have two indices, 0 forms, one index. In 5 minutes, I can just let's check what I said here, that if this B is defined by a closed manifold, well here a closed loop, then B is flat. What does it mean that B is flat? It means that delta B is 0. What is delta B? Delta B is now a 2 cochain, so it associates a group element to every face that is into the end. And then in every face, so first of all, what B is, B puts a -1 on every, let's put it in the color. B puts a minus sign on every link that is crossed by this. So there is a minus sign on every blue link, and there is a plus sign everywhere else. And then delta B is for every phase the product of the signs on the boundary. There's no orientation because it's Z2, so in elements and its events are the same. And you can check that on every phase, you always have an even number of blue edges, just because the surface is closed. So the product is always 1. So B is flat. That's exactly the same thing as what we said before. It's just rephrased in a slightly different way. B is flat. Moreover, B is B is completely equivalent to B plus the addition of an exact 1 form. What would be a lambda 1? Well, a lambda 1 would be a sign defined on each. So what I'm saying is that B1 is equivalent to B1 plus D lambda 0. What would be this lambda 0? Lambda 0 is a value, it's a group element for every side of the lattice. We put a sign everywhere. And then we are just saying that, what is this relation? Delta. This plus also could be, now I'm using a multiplicative notation, so this plus actually means times. And what is delta lambda 0? This means if you are on a particular side, Bij, so this means Bij is equivalent to Bij times lambda I, lambda j. And indeed, if you redefine Bij to be Bij times lambda I, lambda j, then it just means that you've changed the reference point, what it is that you call plus or minus at every side. But you always do it in pairs like this. That's what it means. So indeed, nothing in the partition function, nothing will depend on this choice. So, okay, I hope you see that I've convinced you that B1 indeed is in the first homology group of the lattice, let's say lambda, this coefficient in Z2, exactly in the same way as we saw before. And for every sigma or every more complicated network that I could imagine, I will always have this, provided it's closed. Now the question you might ask is, oh, but what if it's not closed? It's not closed. It's not closed. Actually, I end the line here. Now this is not blue anymore. Now suddenly this is not true anymore. On this face, there is an odd number of minus signs. So I would have kind of so this is kind of an electric line, and at the end I would have kind of some charges. Question is, what are these charges, and what does even charge mean? There is maybe some other symmetry or something like these defects. It seems like there are new defects. They can be moved also topologically, so this is what we will see next time, except that as you can see now, those guys are codimension 2, because sigma was codimension 1. So what we see is that we can introduce these higher codimensional defects, and I will stop very soon, just to say that next time, the next step is to include those guys, codimension 1, codimension 2. And if I take this discussion, but I won't say more now. Next time, I will try to restart from a clear ground, as clear as what it was at the beginning. Now it's a bit messy. And then we will see that those guys here, this codimension 2, they are actually very, very natural objects. Actually, we will start from electromagnetism. And so if you have an that thing, these codimension 2 things would be the symmetry operators for some other symmetry, which is not a zero form symmetry. That would be a one form symmetry, because we've jumped from codimension 1 to codimension 2. And that thing would be kind of the magnetic symmetry associated to our electric symmetry that we have here. So there is this connection to electromagnetism, and that is what we will discuss next time. But now I stop. Thank you. Yes.
Many of the concepts you introduce here in two dimensions are appearing in integrability. So are you going to, I mean, relationship from this?
I would say this is more basic. This is just symmetry. So yeah, in integrability,
Yeah.
you use symmetries.
Yeah, but when you are going to talk about non-local, I mean, generalized symmetries, are there any things which are more specific to?
Not that I know, but I know there is a lot that side of the story. So I don't know, but no, I will not mention connections to integrability. Now the plan is to go to next time will probably be Maxwell theory and study the electrics, magnetic, and electromagnetic duality and so on. And then yeah, we'll move towards the direction of things I know better. So then Young-Mills, QED first, and then Young-Mills. But there will be also a few more things. There will be the gauging will be important. So there will be I will also go back to two dimensions, but yeah, like the Ising CFT and these kind of things, but not the integrability.
Once you have 2D CFT, 2D CFT is an integrable theory, so you have an infinite symmetry.
Yeah.
In this sense, I was asking if there is something which relates the infinite symmetry, which comes with 2D
Yeah.
CFT.
Well, so the point is, okay, I'm everything here I discussed only internal symmetries, so no space-time symmetries. So yeah, I don't know exactly how conformal symmetries actually enter the game. I should have maybe have said more clearly at the beginning. Everything here is internal symmetries. Space-time is kind of in the background. We assume Lorentz invariance and so on, but
More questions? Also online, you can ask questions.
in any case, next time I will just summarize what we've done. In the end, we've just arrived at one definition of symmetry, and from next time we use it and we just start dropping assumptions.
So thank you.